Welcome friends to my YouTube channel. Now in my last lecture I have discussed about the thermodynamic potentials, and there are four thermodynamic potentials, and starting from those thermodynamic potentials I derive Maxwell's relations. Okay, each potential results in each relation. So there are four potentials and we obtain four relations of Maxwell's equation. And so we derive Maxwell's relation by using algebraic treatment, and later we derive Maxwell's relation by using thermodynamic potentials. Now in today's lecture I shall going to discuss about the T and ds equations. Okay, T and ds equation. Now there are three T and ds equations. The first one, at first I am going to prove the first T and ds equation. Okay, so to derive first TdS equation we have to assume entropy as a function of volume and temperature. Okay, we have to assume entropy as a function of volume and temperature. Now since ds is a perfect differential, we can write del s del v temperature constant dv plus del s del t volume constant dt. Okay, now what will be my T and ds? My TdS will be, I write this term first. So T del S del T volume constant dt plus T del S del V temperature constant dV. So what is this? T del S means del Q del T volume constant. This means CV. So CV dt plus T into del S del V temperature constant means del P del T volume constant. Del P del T volume constant. Okay. So this is known as the first T and ds equation. Okay. So this is one form of first T and ds equation. Okay. So this represents the first T and ds equation. This represents the first T and ds equation. Okay, this represents the first T and ds equation. Okay, this represents the first T and ds equation. Now this equation can be expressed in terms of another form, so we have to do it. Okay, so what is the another form of first T and ds equation? So let's check. Okay, what is the another form of first T and ds equation? Okay, so I don't erase this because I need this. Now we all know that what is alpha? Alpha is nothing but volume expansion coefficient, volume expansivity, volume expansivity. And what is the definition? That is increase in volume per unit rise in temperature, keeping pressure constant. So this is the definition of volume expansivity: increase in volume per unit rise in temperature, keeping pressure constant. Okay, so this is alpha, and we all know that it is nothing but isothermal elasticity. It is what? It is isothermal elasticity, and this is nothing but this minus V del P del V temperature constant. Here the significance of minus sign is that as pressure increases, volume decreases, or vice versa. Okay, so if we multiply these two terms, then what we get? This is minus del V del T pressure constant into del P del V temperature constant. And from Maxwell's equation, what we can write? This is del V del T pressure constant means minus del S del P temperature constant. So minus a plus del S del P temperature constant, and this is del P del V temperature constant. So del P cancels. So del S del V temperature constant. Okay, so this is simply del S del V temperature constant, and this can we write as del P del T volume constant. Okay, so from equation 1 can be written in this form, that is T ds this equals to CV dt plus T into, instead of del P del T volume constant we put alpha Et. Okay, so this is the another form of first TNDS equation. Okay, this is the another form of first TNDS equation. Okay, so this is nothing but another form of first TNDS equation. Okay, so this is what about first TNDS equation. So now let us derive the second TNDS equation. Okay, so let's do the second TNDS equation. Okay, so let's do the second TNDS equation. So to derive the second TNDS equation, we have to assume the entropy as a function of pressure and temperature. Remind it. Okay, we have to assume the entropy as a function of pressure and temperature. Okay, now since ds is a perfect differential, this can be written as del S del P temperature constant dP plus del S del T pressure constant dt. ds is del S del P temperature constant dP plus del S del T pressure constant dt. So multiply you both sides by T. I write this term first. So T del S del T pressure constant dt plus T into del S del P temperature constant dP. So what is it? T del S means del Q del T pressure constant means Cp, molar specific heat at constant pressure. And what is it? From Maxwell's equation, what we can write? Del S del P temperature constant means minus del V del T pressure constant. Okay, so this is the known as the second TNDS equation. This is one form of second TNDS equation. Okay, this is the general, but this is the called the second TNDS equations. Now this TNDS equation, the second equation, can also be written in another form. Why? How? Because I told that alpha coefficient of volume expansion is nothing but increase in volume per unit rise in temperature keeping pressure constant. So from which what will be my del V del T pressure constant? That is alpha V. So if we substitute this, what we get? T ds this equals to Cp dt minus T V alpha dP. So this is also another form of second TNDS equation. This is also another form of second TNDS equation. Okay, this is the another form of second TNDS equation. Okay, so this is the called the second TNDS equation. Okay, so now let us do the third TNDS equation. Okay, let us do the third TNDS equation. Okay, so while deriving first TDS equation, we assume entropy as a function of Vt. While deriving second TDS equation, we assume entropy as a function of Pt. And while deriving third TDS equation, we take entropy as a function of P and V. Must remember these things. So while deriving the third TDS equation, let us suppose that entropy is a function of pressure and volume. Okay, so what will be my ds? My ds will be del S del P volume constant dP plus del S del V pressure constant dV. So what will be my TDS? My TDS will be T. We have to rearrange it. We take del T and also take del T here. That means this term del S del V volume constant can be written as del S del T volume constant, del T del P volume constant. And this we can write del S del T pressure constant, del T del V pressure constant into dV. This is V. Okay, so what we get? This is CV into del T del P volume constant plus this is CP into del T del V pressure constant into dV. So this is one form of third TDS equation. Okay, so this represents third TDS equation. Okay, now this can also be written in another form. Okay, so let us see what is the another form. Okay, let us see what is the another form of third TDS equation. Okay, this is simply TDS. Now we all know, we previously derived that alpha multiplied by ET, this is equals to del P del T volume constant. So ET is nothing but, you all know, that is the inverse of KT, and if ET represents the isothermal elasticity, then it is the reciprocal of isothermal compressibility. We all know it is isothermal elasticity and it is isothermal compressibility, so these are reciprocal. So alpha by KT, this can be written as del P del T volume constant. So what will be my del T del P volume constant? This is simply KT upon alpha. So what is KT? KT is this compressibility factor. Compressibility factor. Okay, this is the reciprocal of ET. So this is this, and we all know that alpha is nothing but 1 upon V del V del T pressure constant. So from this equation, del T del V pressure constant can be written as 1 upon alpha V. Just you see. Okay, now if you substitute these values in this equation, then what you get? You get TDS, this equals to CV del T del P volume constant. This is KT upon alpha. This is dP. This is dP plus Cp. This means 1 by V alpha. This is V alpha into dV. So this represents the another form of third TDS equation. Okay, so this represents the another form of third TDS equation. Okay, so dear guys, in today's lecture I derived 3 TDS equations, and while deriving the first TDS equation, we assume entropy as a function of volume and temperature. Okay, while deriving the second, we assume entropy as a function of pressure and temperature, and while deriving third TDS equation, we assume entropy as a function of pressure and volume. Okay, so this we assume. So in case of first TDS equation, we take entropy as a function of volume and temperature. For second TDS equation, we take entropy as a function of pressure and temperature. For third TDS equation, we take entropy as a function of pressure and volume. Okay, so everything is fine. Now what is the significance of these equations? if you are asked that what is the significance of T and ds equations, then you can simply say this equation connects entropy with various physical quantities. Okay, so this equation establishes the relation between entropy S and various physical quantities. So this equation establishes a relation between entropy S with various physical quantities. Okay, it may be pressure, it may be temperature, it may be, you say, alpha, et, these are other physical quantities. So these are directly related with entropy by 3 T and ds equations. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest updated videos based on physics. Okay, thank you.